G'day, in this video, our focus is going to be unpacking thermal conductivity in some quantitative ways. So we're looking at dot points 3.5, 0.6, and 7. We're about halfway through our thermodynamics part of module 3, getting through inquiry question 5, which looks at temperature, thermal energy, and particle motion, the relationships between all of that. Content today is all about thermal conductivity. So what we're going to be doing is some quantitative concepts around how objects can conduct thermal energy. And we're going to be using this relationship here that Q over T is equal to Ka delta T over D, where K is the thermal conductivity of a material. So our two key learning intentions today, we're going to just do a quick review of what we know about thermal conductivity and then actually apply some quantitative concepts and the thermal conductivity formula to some scenarios. So first off, conduction, we talked about this a couple of videos ago, but the general idea of it here is that increased vibration of particles leads to more frequent and higher energy collisions, that these collisions transfer thermal energy through the substance. So what we have here is some atoms which are really close to an energy source. As they pick up that energy, they gain kinetic energy, they start to vibrate more, they collide and transfer the kinetic energy from one object to the next. Here, these collisions are actually elastic, meaning that the kinetic energy of particles is being conserved, meaning that we aren't getting transfer of energy into any other form. It's just passing along and along the chain. Furthermore, we probably already know from junior science topics that metals are really good thermal conductors, but we haven't really spent a lot of time explaining why. So in a metal, essentially all of our atoms are actually positively charged ions. And this is because not all, but some of the electrons which are present on the outer parts of each atom are what we call delocalized. What that means is they are free to move. What that means is they're able to pick up a lot of that thermal energy. They end up gaining kinetic energy and they're able to transfer that further through the object. It actually works quite similarly to the way that we think about electricity. The idea that these delocalized electrons are able to move through the substance, generating an electrical current. Here what we have instead is that these electrons are also able to pick up thermal energy and transfer that energy along the chain, just as the individual atoms are able to increase their vibrational energy and transfer their kinetic energy along as well. So between both the atoms and the electrons, we're able to transfer more thermal energy quickly through the substance. So our thermal conductivity formula we find in our data sheet. Again, it's Q on T is equal to Ka delta T over D. There's a fair few variables in this one, but a lot of them will be quite familiar already. Q is referring to energy. That's the energy that's being gained or lost by the substance. Our little t, as always, is time. In other words, how long is it taking for this energy to move through the substance? K here is our thermal conductivity. And this measurement is unique for every individual substance, depending on how conductive they are. A stands for the cross-sectional area. So here, I guess the idea of having this in as a variable is that if you had a really thin piece of material, you would be able to conduct energy through that a lot quicker than a much thicker piece of material. Delta T, of course, is the change in temperature. And really, this is just the difference between the temperature at the beginning and the end. I'll talk about that in a little bit more detail when we do our practice question. And D is the distance through which this heat energy travels. So some units of measurement here. Q is in joules, time is in seconds, K is in watts per meter per Kelvin. And we'll talk about why that is shortly. Area is in meters squared. Temperature is in degrees Kelvin, and distance is in meters. So the thermal conductivity constants are very similar to specific heat capacity. Each substance has their own thermal conductivity constant, and really this is a measure and indicator of how readily they are able to pass thermal energy through the substance. Keep in mind that there is no information about this in the data sheet. Anytime that you need to use one of these, values will be given. The only time that there will be a thermal conductivity quantitative question where you are not given this thermal conductivity value is if you have to calculate the value itself because you have all the other variables. So the units for thermal conductivity, they seem quite weird given the formula that we have, but we do have the units of K as watts per meter per Kelvin. Now, if we remember, the other time that we talked about watts was when we looked at this power formula. So power was equal to the change in energy over time. So power is measured in watts. And if power measured in watts is equal to the change in energy over time, we can say that watts is a measurement of the number of joules per second. If we reflect on our formula here, Q on T is equal to K A delta T on D, we can then rearrange our equation to make K the subject. So K is equal to QD on time times area times delta T. And from here, I'm just going to convert all of those variables to their respective units of measurement. So Q in joules, D in meters, T in seconds, A in meters squared, delta T in degrees Kelvin. Here we should notice that our meters can cancel out, at least in part, leaving us with joules per second, 1 over meters, 1 over Kelvin. Joules per second is watts. If we're multiplying by 1 over a meter, that's per meter. If we're multiplying by 1 over Kelvin, that's per Kelvin. So let's have a go at doing a practice question. This is just one of the worked examples in Physics in Focus. We're told that given that the thermal conductivity of aluminium is 204 watts per meters per Kelvin, how much energy is transferred through a distance of 40 centimeters in a block of aluminium of a square cross-section of 0.25 meters squared, one side at 60 degrees Celsius and the other at 10 degrees Celsius. That's happening over a 300-second period. So to calculate for this question, let's just draw up a data column first. Note here that for my data column, I have calculated delta T by simply just taking the difference between both temperatures at the ends of the aluminium block. We don't really work in positives and negatives here because it's always being implied in these questions that energy is being transferred from the hot part of the block to the cold part of the block. I've also converted the distance into meters, and that's to match the units of measurement, which is in our K value. So obviously we're going to be using our thermal conductivity formula for this question. And we'll need to rearrange to solve for Q. From here, we can substitute then solve. So note here that I've given my final answer in joules. That is because the thermal conductivity constant was in watts per meter per Kelvin. If it's in watts, watts means joules per second. Therefore, our final answer has to match that. I've also given the answer to one significant figure, and that's because the distance given in the question was only given to one significant figure. Thank you very much. In the next video, we're going to be looking at a concept called latent heat. And latent heat helps to explain what's happening during state changes. But until then, have a good one.